How you doing, DevConf? Yeah? How was day one? Yeah? Good, yeah? Come on, it's all right. You can shout. It's fine. Good afternoon. I have been invited here today to talk to you about something called the art of code. Now, how many of you ever have that thing where you've been trying to fix a problem? You've been trying to get the computer to do something, to run a test or to fix a security bug or something, and you've been stuck. And then you make it work, and the machine does what you told it to do. And you do this. You do that little dance, you do it at your desk, and then you remember you're at work, and everyone's like, why are you dancing? And you're like, I fixed the thing. I made the computer do what I want. And that kind of, thrill, that sensation of having taken a machine and persuaded it to do something that you want it to do happens all over the place. It's what got me kind of interested in software development when I was a kid, like 7 years old. And it still happens to all of us all the time. I hope it does. Certainly it happens for me all the time. And we've heard today talks about architecture and unit testing and rewrites and microservices and all kinds of, important, useful, practical ways that we can build software that helps people deliver services, makes the world a better place, or at least makes somebody a lot of money. Now, I'm not going to talk to you about any of that. I am going to talk to you about code that is useless. There is this quote, Oscar Wilde, all art is quite useless. And what he was talking about is things that they don't solve a problem. They don't serve a purpose. They're created because somebody wanted to make them, to see if they could, or to see how people would react. Now, I don't quite agree with this quote about all art is useless. I like this quote. This is Douglas Adams, paraphrasing Shakespeare. And he says, the function of art is to hold a mirror up to nature, to help us see our world differently. And in order to do this, we need to invent the mirror. First of all, we invented mirrors, and then we've invented all kinds of high-tech systems and things and mechanisms for looking at the world around us. And some of these, they have revealed the most astonishing things about where and how our world works. This is the eye of a beetle. It's absolutely beautiful, taken through an electron microscope. Nobody ever saw this until science and technology invented the tools to let us see it. These are crystals in a dish of soya sauce. This is fluid vessels inside the leaf of a banana tree. And it's not just the microscopic world that we've built machines to help us view and understand. We've built telescopes, and we've sent satellites and rockets into space. We've seen our world. We've seen our solar system. We've even looked into distant reaches of our galaxy. This is 7,000 light years away. It's a thing called the Pillars of Creation and the Eagle Nebula, a photograph taken by the Hubble Space Telescope. And there is another hidden world that human beings had never seen until we built the tools and machines to help us understand it. It's a hidden world of information and mathematics. Throughout the 1970s, Martin Gardner published a column every month in Scientific American magazine where he talked about mathematics and puzzles and games. And the most popular, impactful, reprinted issue ever was October 1970, where Gardner wrote about something called Conway's Game of Life. Created by an English mathematician, a guy called John Conway, Conway's Game of Life was one of the earliest examples of something we call a cellular automaton. Now, as games go, the game of life does not have very much going for it. It's a game with 4 rules, no players, and an infinite board. And the board looks like this. It is a grid of cells stretching off into infinity. And Conway's game evolves according to 4 very basic rules. The rules of life. First of all, if a living cell has 0 or 1 neighbors, it'll die of loneliness. If a cell has 2 or 3 neighbors, it survives. It's happy. If a cell has 4 or more neighbors, it will die of overcrowding. And finally, if a dead cell has exactly 3 neighbors, it'll come back to life in the next generation. That is it. That is the entire set of rules of Conway's game. Now, when the game was first published in 1970, people did this using graph paper. They would sit with a pencil, and they would draw these little diagrams and work out what different shapes would do as they evolved from one generation to the next. And graph paper allowed them to sort of work out what things would do, but it wasn't until people started using computers to experiment with the game of life that we really got some idea what was actually going on here. These shapes you may recognize. These are the tetrominos. They're the things you can make out of 4 square tiles. They're the basis of the game Tetris. And this is how those shapes evolve. This is from Martin Gardner's original article from 1970. Now, this is kind of interesting, but you don't get any sense of what's fascinating about it until you actually run these things and watch them evolve. Now, most of them settle down quite quickly into these stable shapes. But look at this one over here. After 4 or 5 generations, this one goes into this weird alternating looping pattern. Each of these little crisscross patterns is known as a traffic light, because the people who discover things in the game of life give them all these wonderful names. And when you can see this stuff happening, you get a massively different idea about how it works than you would plotting it on graph paper. Very early on, they discovered another configuration in the game of life, something that they called a glider. Now, a glider is a stable configuration, but every time it loops over 5 generations, it moves itself, 1 tile across the grid at a time. And once we had discovered that there were these stable configurations that moved, we started looking for more of them. And once you start plugging these patterns into computers, they discovered some absolutely fascinating things. All of these configurations will move stably across the grid, all of them generated by those 4 rules, same rules of the game of life. They're called spaceships. There are whole fleets of these things out there. Now, one of the early questions that was asked is, are there grids in life that will just grow forever, infinitely, keep growing? And in the 1970s, in 1970, in fact, there's a guy called Bill Gosper who was experimenting with configurations and gliders and things. And he created, invented, discovered, I don't know what the right word is, but he found this. It's a configuration called Gosper's glider gun, which bounces backwards and forwards, and every time it does, it sends a glider with infinite stream of these gliders out across the grid and into infinite mathematical space. And he also discovered a configuration called the eater, this thing, bottom right-hand corner, that will absorb these gliders. Now, what's fascinating about this is we basically now have a way to generate a signal and a way to remove a signal. We have 1, we have 0, true and false, yes and no. Can we do more with it? Are there ways to get these signals to interact? It turns out, yes. This example here, these highlighted areas, imagine that those are some kind of signal detector on a grid. And we've got 3 generators in here. What we're going to do is build a logic gate. So if we open up signal from source A here, we're getting signal flowing through there. That's green. But then it's interfering with the other stream. Nothing is getting through. Remember, we're looking for our output here, bottom corner. Now, as soon as this circuit gets up and running, 0. But if we go through and we enable both inputs, A and B, and start our circuit flowing, what we get is output. Using those rules of the game of life, we've built an AND gate. And if we can build gates, we can build circuits. And if we can build circuits, we can build computers. And if we can build computers, we can run programs like this one. It's a program called Conway's Game of Life, running on Conway's Game of Life. Now, I think this is just mind-blowing. It's absolutely mesmerizing. And it is completely useless. This doesn't solve a problem for anybody, but look at that. Isn't that beautiful? Now, the game of life automata is one of a whole category of problems and puzzles and areas of research that have something in common. They take a very, very simple, what looks like a simple set of rules that can produce incredibly complicated behavior based on minor differences in their inputs. You may have heard of something we call the butterfly effect. Now, there were a whole bunch of fields in the 1970s, mathematics, weather forecasting, geometry, computation, that all kind of got a feeling maybe they were converging on the same thing. This is something we now call chaos theory. And the butterfly effect came from this observation about long-range weather forecasting, that if a butterfly flaps its wings in Rio de Janeiro today, in 2 weeks' time we might have rain in Tokyo instead of sunshine, which is why long-range weather forecasting is basically doomed. We can tell you that summer will be warmer than winter, but we can't tell you when it's going to start raining on Christmas Day because we just don't know. We can't measure the inputs precisely enough. And this field, chaos theory, yielded all sorts of interesting research, and one of the most fascinating things that chaos has delivered is a field called fractal geometry. Now, in order to understand fractal geometry, you have to get your head around some pretty weird mathematics. Let's take a grid, graph paper like we have in school, and we're going to draw some squares on it. So we're going to draw this square here, which is 2 by 2. What's the area of that square? 4. Now, indulge me a second. We're going to draw another one, but we're going to draw it over here. So this square is effectively minus 2 by minus 2. What's the area of that square? 4. 2 times 2 is 4. Minus 2 times minus 2 is also 4. And so at various points in history, someone has popped up and went, well, if minus 2 times minus 2 is 4, what can we multiply it by itself to get minus 4? And we proved this was impossible. And for engineers and physicists and everything, that's the point where you kind of go, all right, fine, we're done. It's impossible. Thank you very much. Let's move on. But that's not how mathematicians work. Because mathematicians just scribble things on whiteboards and see if they're consistent. And so mathematics turned around and went, well, yeah, we know it can't exist, but what if it did? What if we just wrote down that I squared, we'll call it I because it's imaginary. We made it up. But if I squared equaled minus 1, what else could we do if we just accept that that thing there is true? And what they had created is a field called complex numbers, complex arithmetic. Now, this thing here is something we call an Argand diagram. It's basically a map of all the possible real and imaginary numbers. The real numbers run from left to right. Those are the numbers that you have on restaurant bills and bank accounts and fuel tanks. Those are the things which we can count in the real world, positive and negative. The imaginary numbers are all the things that multiply to make negative numbers, the stuff we've just made up. And we can plot any point over here. That's actually too far for my laser. We can plot any point on this graph as what's called a complex number. Now, a complex number is like a project plan. It has a real part, it has an imaginary part, and you have no idea what's going to happen just because you have one. So, what we're interested in, let's take this point here, 0.8 plus 1.2i. We want to multiply that number by itself. Now, the way you do this is basically, it'll be familiar to anyone who did high school arithmetic. We want to take that number and square it. Now, I've color-coded the real and imaginary parts here. So we're just going to expand that out and say, all right, well, it's this plus this times this plus this. And then we can reconfigure that. We can say, well, let's put the real parts over here and the real times imaginaries in the middle. Now, remember, imaginary numbers times imaginary numbers become real again because that's what they are. That's how they were invented. So in this thing, anything where they're the same color, we're going to get a real number. Anything with red and blue in it, we're going to get an imaginary number. And we sort of crunch the whole thing round a couple of times, and we end up with a result. And we can say, right, the square of that number at the top is that number at the bottom. And people say, how do you know? And we say, well, it just is. Look, we worked it out with colors and everything. Now, there was some work done in France at the beginning of the 19th century by two guys, Gaston Jullien and Pierre Fatou, on the iteration of rational systems. They were mathematicians, but they were not necessarily interested in solving equations. They wanted to understand what happens if you just keep crunching the equation round and round and round. And for the real numbers, let's say we're going to take some number x, and we're going to say, right, every time round, x equals x plus 1. So there we go, x equals x plus 1. Okay, fine, yep. And you can see quickly, intuitively, you develop a feeling for how this system is going to behave, right? X equals 2 minus x, all right, well, it goes to 2 and then back again. And then 2 minus 2 is 0, and round we go. And you very quickly get these stable patterns of behavior. Now let's do the same thing, but with a complex number. We're going to take this number here, and we're going to, every iteration, we're just going to say this number goes to this number squared, okay? So first of all, it goes from there to there. And then we square that number, and it gives us this. And we square that number, and it goes to here, and we square that number, and whee, it's heading off, and it's gone. That number is now diverging towards infinity. It's never coming back. I'm going to pick another one. which is just next door to our original starting point. And we're going to do the same thing. And it's going to go round and round. And now this one doesn't go diverging off to infinity. At least we don't know if it does. It hasn't done it yet. It's getting into this sort of weird, stable orbit somewhere around the origin of our graph here. Those points are almost exactly next to each other, but they have dramatically different behavior when we keep crunching them through this algorithm. If we plot half a dozen different points, these colored lines all started within 0.1 of each other. The green one has gone off to infinity, but it hasn't, because at some point it's come back and then vanished again. The blue one is galloping off towards... By the way, we have 4 different kinds of infinity on this graph. We've got real positive infinity, real negative infinity, imaginary positive infinity, and imaginary negative infinity. So the blue one there is galloping off towards real positive infinity. The red one's going round and round. The purple one has basically dived in on 0 and is just rattling around in the middle of it. And Gaston, Julien, and Fatou, they had kind of realized something weird was going on. But they were working in 1918. They were using pens and paper. To crunch one of these points and plot that graph would have taken them a couple of hours. So they knew they'd stumbled on something, but they didn't have the tools to really, really get a glimpse and an insight into what was going on. We didn't get that until this guy came along. This is a Polish mathematician, actually. Poland represent. Benoit Mandelbrot. He was a mathematician, born in Poland, lived in France, spent most of his life working in the United States. And he was fascinated by the science and the mathematics of nature. He had this lovely quote: "Clouds are not spheres, mountains are not cones, coastlines are not circles. Bark is not smooth, nor does lightning travel in a straight line." He wanted to understand the maths of things that were real, things out there in the world we could touch. And he was experimenting with the same kind of ideas as Julia and Fatou, but he had 2 things that they did not have access to. First of all, he was working at IBM and taking frequent leaves to go and teach at Harvard. Now, that sounds like a brilliant job. Like, he'd go to IBM, all the computers, he'd go to Harvard, spend a couple of months hanging out with some really, really smart people. They'd have a good idea. He'd go back to IBM and go, "Hey, can I borrow the computers?" Because IBM had all the computers in the world at this point. And then he'd go and try it again. So one thing, he had access to computing power that nobody had ever had before for these kinds of problems. But he also had an idea. What if we just feed the same number back in, and every time z goes to z squared plus z, whatever the number we started off with is. And he iterated through this sequence over and over again using these IBM computers. What he was doing, you pick a point on your plane and you iterate it. And if it disappears off to infinity, you leave it blank. And if after a certain number of cycles it hasn't disappeared yet, color it in. Now we're talking color it in meant print an asterisk at that point on the graph, which is what they were able to do, and so that is what he did. In early 1980, he became the first person in history to see this, which everyone calls the Mandelbrot Set because it was invented by Mandelbrot. So pronunciation is hard. Now, nobody had ever seen this thing before. Was it invented? No, it wasn't. It was discovered. This is a natural phenomenon. It just emerged from the mathematics when we had computers powerful enough to work with it. In the 90s, computers got fast enough we could start plotting this stuff in color. And the way that we did that is you pick a square, and if it goes straight to infinity, it's pale blue, and if it goes a little bit slower, you make it a brighter blue, and the ones that take a little while to get there, you make purple and red, and the ones that never go to infinity, you leave those black. So the black cells here are the Mandelbrot set, the set of numbers that do not tend to infinity. And this is kind of what it looked like when I was drawing this on my 286 PC in the 1990s. When we draw these things now, they look like this. And the astonishing thing about the Mandelbrot set is that it is infinite. There is no limit ever to the amount of detail and complexity. One equation, z goes to z squared plus z, and we're going to zoom in on this one. So that is our starting Mandelbrot set. Now we're going to keep zooming in. So at this point, that original set there is approximately the size of that cinema screen. We're going to zoom in. Around about now, we're getting to a factor of about 10 or 15. So the original one is now roughly the size of this cinema complex. 20, the original shape we drew there is now the size of the city block. Around about this point, our original fractal is bigger than Krakow. We're going to keep zooming in. Around about now, it's bigger than Poland. At some point here, now imagine we're standing on a printout the size of Europe, and there is still this much detail sitting right at our feet. And we are just going to keep zooming and keep zooming and keep zooming. Now, at this point, I'm going to pause the zoom because we found quite a nice place to stop. But this thing goes on forever. There is this infinite level of beauty and detail and complexity hidden inside that one equation that nobody ever saw until we developed the computers and the software that allowed us to visualize it. Now, some people have called this Mandelbrot set the thumbprint of God. I'm not a very spiritual person, but I do play a lot of computer games. And I love that thing you get in a computer game where you're worried you might be, like, not on the right track, and then you find an Easter egg, like a little something that was hidden in the game to say, it's all right, you're on the right track. Look, you were supposed to be here. Keep going. Now, in order to see this, we had to invent imaginary numbers and complex arithmetic and figure out how to work with it. And then we had to invent computers that were fast enough to crunch the billions of calculations that were necessary to draw this thing. And there it was, you know. This was not invented. This was discovered. This is hidden inside the reality of the universe that we live in. I think that is really, really cool. Now, there was a day when you could show someone something on a screen and it would be impressive just because it was on a screen. You know, where computers, nobody had ever seen graphics on a computer before. And you'd be like, look, I drew a picture of my face. And they'd be like, that doesn't look like your face at all. Those days are gone. Computer graphics now does pretty much everything, all the time, everywhere. 1982, Disney came out with the movie Tron, which was this amazing fantasy about getting sucked into computers. Tron did not win an Academy Award for Best Visual Effects because the Academy, the people who give out the Oscars, said that using a computer to make a film was cheating. And they were not going to let people do that. And so obviously, everyone went, all right, well, we're not going to use computers to make films anymore. That would be cheating. No, they didn't. We can do pretty much anything with computers now. Pixar made Luxo Jr., the first completely computer-animated film. Jurassic Park's dinosaurs, the first living creatures interacting with human actors on a film score. A couple of years ago, Lucasfilm, now there's some controversy here. Lucasfilm said that they created a digital Grand Moff Tarkin, who is a fictional character. And lots of people went, you've created a digital Peter Cushing. He's a real actor and he's dead. And I don't know yet what the outcome of this is going to be, but we're getting to a point where if you want to put an actor in a movie, you don't need the actor. You just find some photographs of them, and you feed them into a computer vision system, and you say, hey, show me what Friends would have looked like if all the parts were played by Nicolas Cage. And you get this. And it's kind of creepy and kind of freaky. But this is the kind of things we can do now. Now, you know, this has implications for all kinds of things. Politics, show business, news, media. You know, when someone can make a video of anybody doing anything to anybody else anytime, how do you know what to believe anymore? But as well as the kind of scary deepfake side of things, this sort of machine learning has also given us something else that I think is really quite cool. You ever lie on your back in a field on a sunny day and you're watching the clouds and you're like, oh, look, there's a rabbit, and that one's a dog, and there's a bike, and there's my mother-in-law, and, you know, your brain is watching these shapes. And it's filling in the gaps, and it's making them into things for you. This is the pattern recognition system which drives the human brain and which we have been investing huge amounts of energy and money in trying to get computers to do the same thing. And we're getting pretty good. We've got these things now called convolutional neural networks, where we take a machine, we don't know quite how it works, but we give it like 1,000 cat pictures and 1,000 dog pictures, and we say, go and learn the difference between a cat and a dog. And it comes up with all sorts of layers and algorithms, and it looks for noses, and it looks for lines, and it looks for fur, and eventually you have a machine or an algorithm that you can give it a picture, and it'll tell you, is it a cat, or is it a dog, or do you not know? We've basically invented a dog detector. Now, what happens if you take a dog detector and you turn it around and you crank up the power and you turn it into a dog amplifier? And then you give it a picture that does not have any dogs in it, and you say, find the dogs. And the machine goes, I can't find any dogs. You say, I don't care, find the dogs, look harder, there are dogs. And it goes, all right, I found some dogs. And you go, amplify the dogs, turn up the dogs. And it goes, all right, I don't know what we're doing, but okay, I'll do what I'm told. And you get pictures like this. Now, the first software to do this came out of Google in 2015. It was called Deep Dream. And so this whole image convolution technique is called deep dreaming. And it's freaky, isn't it? It's like walking through a forest at night where all the trees look like a monster until you look at them. You're like, no, it's just a tree. And you kind of get some insight. You know, this is the networks have learned to recognize dogs, and then we've fed that into a feedback loop and told it to exaggerate those characteristics, even if they weren't really there to start with. Find the closest thing you can and literally crank up the dog to 11 everywhere you can find one. And yeah, this is called deep dreaming. And it's weird, and it's unsettling, and it's beautiful. And we would never have seen any of this if somebody hadn't gone, hey, what if I train a computer to recognize dogs and then switch it backwards and turn the power up? But we did, and that's cool, and I'm glad that we did. Now, I think computers and software are going to give artists some amazing possibilities. I have this little clip. This is Raphael Laguerre painting his house. So that's Tiltbrush, 3D artist tool, basically, that's coming out of Google for use with VR headsets. Now, I can't wait to see what people come up with when augmented and virtual reality are in everyone's hands. Some people are going to use it to make money. Some people are going to use it to solve problems. Some people are just going to do cool stuff with it, just to see what they can make it do. But we've talked enough about using computers and software to make art. I want to talk about software that is art. Now, we've debated for years whether software is art or engineering or science, or whether we could have production line factories for computer programs. But I'm sure if you're anything like me, at some point you've been asked to review some code, and you've looked at it and you've gone, this is not engineering, this is not creative, this is not craft, this is not art. I don't know what this is, but it's nasty and I don't like it. And when that happens, like at work, from professional developers, it's not a good idea, and you kind of have to take someone out for a beer and say, maybe the whole computer thing isn't really the right career for you. But there are places out there that does this kind of thing on purpose, and one of the most famous is the International Obfuscated C Code Contest. The goals of the contest are to write the most obscure C program, to show the importance of programming style in an ironic way, which means don't do this, we did this, but you don't do this, to stress compilers, to illustrate subtleties of the C language, and provide a safe forum for poor C code. I want to show you an example. This is the complete source listing of a program that was submitted in 2015. Isn't that lovely? That's the whole thing. And you know what we get if we run it? Let's try. So we're going to run the makefile, we're going to run the program, and there it is. Look at that. It's Flappy Bird running on a Unix terminal in 1 kilobyte of source code. And it is no easier than Flappy Bird is anywhere else. I'll show you another example. Someone gives you this in a code review. And you're thinking, well, that is probably just about the ugliest code that I've ever seen in my life. But watch what happens when you zoom out. This is a Mandelbrot Set generator written in C, shaped like a Mandelbrot set. Because why not, you know? We can. It's not against the law. Don't put it in production. But I think that's brilliant. I love it. Especially the little return 0 hovering right down at the bottom here. It's like, yeah, we're done. Now, there was a submission in about 2001. Somebody wrote a chess engine in 1 kilobyte of C. And recently they ported it to JavaScript. And this is the entire source code, including graphics, of a thing called nano chess, written by a guy called Oscar Toledo G. Now, this is the whole thing. You paste this in a browser, and you click F5, and it does this. And I don't mean it draws a chessboard. I mean this beats me at chess. This is a chess engine with an analytics engine and a rule engine and a complete GUI and a board and all the UI necessary to play a game of chess. I just think that's awesome. Oscar Toledo G has won the International Obfuscated C contest about 5 times now. And, I love it that there are people with that much talent and that kind of appreciation for just doing whimsical things to see if they can. I want to show you a submission from the IOCCC in 1994. It was this. And it got an honorable mention. This is an empty file. And the person who submitted it, Simon Rasinkiewicz, said, I've got a C compiler that if you give it an empty file, it creates a program that produces empty files. So this is a valid C program that prints its own source code. And they went, all right, just this once, we will let you win. And they introduced a rule that all programs had to be at least 1 character after that, which I think is sensible. But this gets us on to something called quines. Now, a quine was introduced in Gödel, Escher, and Bach, Douglas Hofstadter's amazing book about maths and art and music and all kinds of things. A quine is a program that prints its own source code. Now, that doesn't sound that complicated, so let's try building one in C#, because that's what I was using. So we got a C# class program with a static void main in it. Now it needs to print its own source code. So we're going to console.writeline class program and console.writeline static void main. And now, well, hang on. Now we need to print the source code that prints the source code. So we're going to console.writeline a console.writeline the class program. And very rapidly you start going cross-eyed because you're like, I can't, we've hit this infinite recursion loop very easily. So let's backtrack a little bit. Let's jump in here. What we're going to do is put our program in a variable. And we're going to then do something clever with the way we print it. So we're going to put in our class program and our static void and main and all that kind of stuff. And then we're going to exploit a little quirk of C# and .NET, which is a thing called string templating, where you can put placeholders in a string, and then when you print it, you can say replace those placeholders with arguments. So we're going to say var s equals 0, 1, 0, so the first, the second, and the first argument, and then we want you to write line that. Now, the char34 here is a quote character, double quote in ASCII, because we can't quote quotes, because if we quote quotes the first time, we need to quote the quoted quote the second time, and the third time we need to quote the quoted quote. You see the problem. And then we're going to do a console.writeline, and we're going to feed that template string back into itself as its own second argument, and this program will print its own source code, which I think is kind of cool. Now, some languages are better at this than others. JavaScript functions have a toString. So a JavaScript quine is just f.toString, and that gives you back the function you just ran, and you run it, and it gives you your function back again. Now, obviously, this is useless, because if you've got your function, you don't need to run it to get it back, but I think it's kind of neat. Now, I was reading up about this, and somebody told me in ECMAScript 6, this is a valid quine, and I said, don't be ridiculous, that looks like noise. So I pasted it into the console, and sure enough, that is a JavaScript expression that prints its own expression code. Do you think we can make a quine in HTML? So here's source code for a web page. Yeah? HTML, head, title, blah, 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 blah. And when we run it in a browser, it looks like that. Inspired by Leon Bambrick, is a guy from Australia who does brilliant things with computer art. You should all check him out. Now, first thing we're going to do is something you will never, ever do on a production website, which is we put in this rule, which says we want everything in the markup to be displayed as a block. Everything. Even stuff that you're not supposed to see, like the CSS, the style sheets. And then we're going to come back over and go, all right, well, let's take the HTML tag, and before and after, we're going to put HTML, open, closing tags. This is still valid CSS. We jump back over again. Now, /HTML is actually down here somewhere, because it knows to draw it, but it doesn't know where to put it. So it's gone off the bottom of the viewport. So we're just going to kind of replicate that pattern. Let's put style at the beginning and end of the style block there. Now, you'll notice we can't put /style inside a style sheet, or the browser chokes on it, but we can escape it with a backslash. So we plug that in, and we refresh our page, and it's starting to look a little bit like its own code. Now, there's no way to generate all the before and after rules we need, so we just need to kind of bolt those in by hand. Before, after, before, after, before, after. You get the idea. But that gets us to this point. Now, the last thing that's missing here is that this A, anchor, the link tag down here, should be showing its href so we know where it's going. And we can do that using CSS as well. We can say, all right, if you find an anchor tag that has an href, then we want you to put some content before it by pulling out that attribute and putting it into the markup of the page. And there we go. So now we've got the text of that, all in CSS, in the original page itself. I'm going to add one more rule in here, which is just, we're going to put a margin on it, and we're going to hack the height so that HTML comes up off the bottom of the screen there. And we've built a web page that is its own source code that you can paste back into itself. Now, obviously, this is completely useless. Why would you ever need this? But I learned a bunch of stuff. I've been building web pages for 15 years, and I learned stuff I didn't know about HTML by following the things I found about this and putting this together. So that's kind of cool. Let's look at some really fun stuff. What language is this written in? C or C++? Okay. So what I'm going to do is I'm going to apply a C syntax highlighter to it, and I'm going to just fade out anything that C thinks is a comment. I mean, it's not brilliant C, but it's C, right? It kind of works. But what if we run it through a Ruby parser and filter out things that Ruby thinks is a comment? And let's just highlight the string literals to make it a little bit easier. This program prints its own source code in C, C++, Perl, Python, and Ruby. Now, I know that sounds like lies, right? So watch. This is it. So we're going to cat polyquine.c, and there it is. And now we're going to run that through GCC, and we're going to get an output. Now, we got a warning, but hey, we don't care. We're not going to ship this in production, right? And there it is. And now we're going to take that original C code file, and we're going to run it through Ruby. So we're going to type ruby polyquine.c, and it is going to print its own source code. And now, because, hey, why stop just when we're getting warmed up? We're going to run the same thing through Python, and there it is. And now, I had to install Perl on my laptop for this in 2019. I'm going to run that through Perl, and there it is. It prints its own source code. And if you can find a C++ compiler that's old enough that it doesn't care about main not returning an int, it's valid C++ as well. And we're not even getting warmed up. Check this out. What language is this written in? Well, let's dig into it a little bit. So we've got a system.console over here. So it's probably C#, right, or .NET. But this thing here is an XML namespace. That's a for each and a console.log, so maybe some sort of JavaScript-y stuff going on there. Are there any Ada programmers in the room? This is an ada.textio.procedure, whatever one of those is. It sounds important. That's a begin, all in block capitals, so probably COBOL. And up here, we've got Act 1, Scene 1, Enter Ajax. What? This is one of the most amazing things I have ever seen. It's written by a guy called Yusuke Endo, who is one of the Ruby language core contributors. It is a quine that is, it's called an Ouroboros quine. It is a Ruby program, and when you run it, it prints a Rust program. And when you run that, it prints a Scala program. And when you run that, it prints a Scheme program. And it goes right around through 128 languages to Rex, and then the Rex program prints the original Ruby source code out again. Now, there are two things about this that just make me think some people have got way too much class. One, it does it in alphabetical order, because of course it does. And two, the source code file for this, the thing that gets recreated at the end, looks like that. And a month ago, and this is the part I love, these 128 languages, there are Ubuntu packages for all of them. They are all available on Aptitude, and so there is a continuous integration server for this that spins up a Docker container using GitHub Actions, installs all 128 languages, and gets as far as, yep, done, it works. Now, let's rewind a bit. What was that Act 1, Scene 1, Enter Ajax and Forward? What was going on there? This is a programming language called Shakespeare. Shakespeare is an esoteric language that is designed to write programs that are also plays. Now, why would you do this? Who cares? That's not what we're here to talk about. How do you do this? Now we're talking. That's interesting. This is Hello World in Shakespeare. Now, in Shakespeare, you have to introduce all of your variables who have to be named after Shakespeare characters. So we have Romeo talking to Hamlet. Act 1, Hamlet's insults and flattery. Scene 1. Now, the way Shakespeare works is that adjectives put values into accumulators. Accumulators go into the variable represented by the person who's being spoken to, and speak your mind makes them output whatever their value is. So Hamlet says, "You lying, stupid, fatherless, big, smelly, half-witted coward, you are as stupid as the difference between a handsome, rich, brave hero and thyself. Speak your mind." And we get H. And then he says, "You are as brave as the sum of your fat, little, stuffed, misused, dusty, old, rotten codpiece." And at the end of that block, we'll get E and L and L. Now, this is not a terse language. Shakespeare wrote long plays, so I think it's okay that Shakespeare programs are long programs. And when you run, so this bit on the screen will just print hell. But if we had a bigger screen, I could get the whole of Hello World up there. And we can get even bigger ones. Here's another Hello World program. Now, this is a real program. This isn't a blank joke program. No, this is a serious program written in a real programming language called whitespace that ignores everything except spaces, tabs, and line feeds. Everything else is a comment. If we color code this, that's what the source code for this file actually looks like. Now, whitespace is brilliant for hiding programs in other files, because you can put anything you like in there. You can hide whitespace inside C and C++ files, and as long as the tabs and spaces are in the right place, they'll run, and they'll ignore all the real code. That's one of the languages in the 128-language Ouroboros quine. Now, this is a programming language called Chef, which is designed to write programs that are also recipes. This is Hello World, 72 grams of beans, 100 eggs, 111 cups of oil, 33 potatoes, and 32 zucchinis. Now, the thing about esoteric languages, and the whole idea of esolangs generally, is they introduce a set of constraints for programmers. The challenge is, can you create something which is a real computer program, but is also a real example of something else, something that has behavior or correctness or beauty from some other sphere of human endeavor? And somebody took a look at this Hello World recipe in Chef and went, okay, fine, but actually that's crap. I don't want to eat that. I'm going to make a Hello World recipe that actually works. And they did. So this is a programming language that if you run it on the Chef compiler, prints Hello World, but if you run it on your kitchen, you get a chocolate cake with chocolate sauce, which apparently is a little dry, but actually quite good. I think that's really cool. Show you one more language. This is a language so weird it might not even be a language at all. We're not sure. It's how you square a number in the language called Pete. Pete is a graphical language. Here is Pete's instruction set and constants. And basically, you have a little cursor which crawls across the source code, which is a GIF. And when it passes between boundaries of color, depending on the change in the lightness and the change in the hue, it generates one of these instruction codes. So this is how you square a number in Pete. The instruction pointer starts there. When it crosses from light blue to dark green, that's an input instruction. It then hits a black wall, it turns 90 degrees right. It heads south. When it passes from green into red, that says duplicate. Take the value that's on the stack and duplicate it into the next thing. When you cross from red into yellow, that means multiply. Pop the top two values off the stack, calculate their product, put that back on the stack. We cross from yellow back into red, that is an output instruction. Print out the result of squaring that number. Jumping across white is a no-op, because anything involving white is a no-op. And then when you get to that blue area there, the pointer flows through the blue as far as it can, ends up with black on all sides, which means it can't change direction, which means halt. Program's terminated. Now, Pete, named after Pete Mondrian, the Impressionist painter. Pete is just wonderfully weird. And here is a Hello World example from Pete, which I think is beautiful. And it's, this is a real program that runs. You can get stuff out of it. But it's also kind of artistically pleasing. It's kind of nice. Okay. Now, up until now, we have talked about the idea of writing programs and giving them to somebody, and somebody else goes and appreciates them. What about code as performance? What about something happening in real time? Now, in software, we hate anything you can't do twice. Everything should be reproducible. Unit tests, integration tests, infrastructure automation, infrastructure as code, total reproducibility. And we have this term, snowflake, for, that server you have in the office, the one that's got all the weird service packs on it, and you can't install Windows Update or your finance programs won't work because it's unique. It's one of a kind. There's nothing else like it anyway. We talk about this idea of a snowflake server. But snowflakes are also beautiful. And if you catch a snowflake out of a blizzard and you watch it melt on your hand, you've just been part of something that nobody else will ever see because no two snowflakes are ever alike. So what about the idea of software as part of a unique experience that cannot be reproduced with automation and unit tests? This is the London Philharmonic Orchestra, and the guy in the middle there with his laptop is Sam Aaron, who is the creator of a thing called Sonic Pi. Sonic Pi is a programming language for doing live music performance. Basically, you write code, the code runs, and when it runs, it doesn't produce output, it produces music. I want to do a very quick demo of this for you now. So fundamentally, we say play A4, it plays that note. In Sonic Pi, everything happens at the same time unless you introduce latency. It's the only language in the world which is parallel by default. Now we're going to go and put in this use BPM. We're going to put in something with a tempo, and we're going to plug in a couple more notes here. So we're going to run a loop. We want to do this thing 16 times. There we go. Now that's not the most exciting melody in the world. So what I'm going to do is I'm going to take that and I'm going to wrap it up. I'm going to put a variable in here, and I'm going to check the value of that variable because I want to see if it's divisible by 3. And if it is, I'm going to play this note. Otherwise, I'm going to play a different note. And then I'm going to increment I. I'm going to run that program. Now that's starting to sound a little bit like something, isn't it? Now the great thing about Sonic Pi is you can wrap your code in blocks, which are called live loops. And you wrap your code up in a loop, and then it will keep running and reloading it, and it won't lose time. It won't get out of sync. So we can keep this loop playing live in the background, and we can go and drop in and out, and we can plug in other things. We can add other capabilities to our program while this loop is going round and round and round. So I'm going to drop another loop in on top, and I'm going to say this loop should be synced to my loop. So every time that one starts, start one of these as well. Play them together in parallel. And then 3 times, I want you to play this. I want you to play a sample, and this sample is going to be called the drum cymbal closed, and then I want you to sleep. And then I want you to plug in one more sample at the end there. So I'm just going to copy that, drop that in under there. We'll do 15 of those. And now when I reload it, it doesn't drop a beat. Nothing has to stop and be recompiled. It's rebuilt the program code in real time and is actually playing it out live as we're performing. So now we're going to drop in another loop on top of that. And this one, we're going to start putting in some drums. We're going to go in, we've got a sample in here of a heavy kick drum, and we've got a sample in here of a hard snare drum. Wait and see what happens when we plug this in. By the way, I'm going to overrun by a few minutes. Is that all right? I can stop now if you like. That loop, we reload the whole lot. We've made a mistake. We've forgotten to declare it as a symbol. There we go. And we can do this in real time. So now I'm going to introduce a little bit more behavior. I'm going to say, if I divide by 5, I want you to play this note. Otherwise, if I divide by 3, I want you to play this note. Otherwise, I want you to play this note. And finally, I'm going And I want to finish by telling you about my contribution to the world of people doing idiot, stupid things with computers. Because last year, Paul Stovell, the founder of Octopus Deploy, put this on Twitter. To really confuse recruiters, someone should make a programming language called Rockstar. Because you know the whole Rockstar developers, right? I hire a Rockstar developer. And I thought, that's a brilliant idea. This is what I have to do. This is why I was put here. I know now what the world needs. I know what has been missing. Because when I wasn't wasting my youth writing Mandelbrot sets on 286 PCs and stuff, I was wasting it listening to bad music made by people with large hair. And I decided what the world needed was a programming language for writing 1980s power ballads that were also valid computer programs. So what I did is I did what everyone does. I went to a bar and I wrote a language specification. I sat there with my laptop, I had a couple of beers, and I wrote a parody spec for a language called Rockstar. And I came up with a couple of ideas for it. So Hello World, I was like, we need I.O., but I want you to be able to kind of put a little bit of emotion into the thing. So you can say Hello World, but you can also scream it or whisper it or shout it, depending how you're feeling. Because this is rock and roll, and you want to be able to put your heart into it. Now, variables and assignment. Most programming languages have stuff like int x, var myString, the message equals hello DevConf. Now, there's a lot of stuff in here which isn't going to work in a song. For starters, we're dynamically typed. We don't need ints and vars and things. And get rid of the semicolons, because I never understood what they're really for anyway. Now, we've got this equal sign, which looks a little bit like maths. And that's not going to work with rock and roll. That'll do. X is 5. My string is hello world. The message is hello DevConf. Now, I saw a talk that Douglas Crockford, who the creator of JSON, gave, where he was talking about the next generation of programming languages. And he's like, have you ever had an argument with your team about underscores versus hyphens versus Pascal case versus camel case? And everyone's like, yeah, you know. What we want is variables with spaces in them. Well, hell, I'm inventing a programming language in a bar. Of course we can have variables with spaces in them. So I plug in this. Simple variables. Common variables are my, and, your, a, the. So you can have my heart, an ocean, your dream, a kiss, the night. And proper variables, anything starting with capital letters, that's fine. Dr. Feelgood, yeah, valid variable. Black Betty, Billie Jean. Now, to write computer programs, you often need to load numbers into variables. And numbers are not very rock and roll apart from that awful Billy Ray Cyrus thing. I wanted a way of putting constants in that didn't have to be numbers, so I came up with the idea of what I call poetic literals. We take the is operator. You take the right-hand side of the line and you count the digits in the words. And you treat the digit count the letters, modulo 10, that gives your digit. So here we've got phys is ICE, 3. Dying, 5. A love-struck lady killer, 1. 10 modulo 10 is 0, 10 modulo 10, 100. There's more. We want to do floating point numbers in C#, decimal pi, in JavaScript, var pi equals 3.1415, blah, 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 blah. In Rockstar, my heart was ice, a life unfulfilled, waking everybody up, taking booze and pills, is how you load pi into a variable. 3, ice, ICE, dot, and then it just counts the word lengths. We need a way of doing arithmetic. Now, I didn't want plus and minus signs and that kind of stuff, but I figure English, we have ways of talking about this. The price with the tax, that's the summation. You talk about something without something else. The total without the tax, that's a subtraction. The quantity of the product, well, that's multiplication. The distance over the time, that's division. But it means we can write equations like a girl with a dream, a man without a face, the wings of the night, a whisper over the water. We need comparison operators. All right, your love is a lie. Well, is it true or false? Your love is a lie. The whiskey ain't the answer. True or false? My heart is stronger than steel. My soul is weaker than water. My will is as strong as a lion. Your lies are as low as a snake. Needed a way to write functions, because you can't program without functions. And so I came up with this syntax. Modulus takes a number and a divisor. Function name, 2 arguments. While a number is as high as a divisor, put a number without a divisor into a number, give back a number. So there you go. Just keep knocking it, subtracting until it reaches a threshold and then return it. It's how you do arithmetic modulus. But if you want to really put your soul into it, midnight takes your heart and your soul, And while your heart is as high as your soul, put your heart without your soul into your heart and give back your heart. So I kind of wrapped this up, and I paid my bar bill, and I stuck it on GitHub, and I put a tweet out saying, hey, look, introducing Rockstar, a proposal for Turing-complete programming languages. And it went crazy. I got 2,000 GitHub stars in 24 hours. It made it onto Hacker News. It made it onto the front page of Reddit. Cory Doctorow did an article about it for Boing Boing. There were comments, like just all kinds of people. And everyone loved it. Like, everyone kind of got the joke and was completely behind it, saying, this is brilliant, I love it, it's genius, I want to be a certified Rockstar developer. I'll tell you about that in a second. Shut up and take my money. Then I got an email from Classic Rock Magazine, which is a proper rock magazine that interviews proper musicians like Guns N' Roses and Metallica, saying, what's this Rockstar thing we keep hearing about? And so I got in Classic Rock Magazine for inventing a programming language in a bar, which I don't know if that's cool or not. I mean, maybe that's why I'm happy being in Classic Rock Magazine. But then the weirdest thing happened about 3-4 days later. People started filing issues on the GitHub repo. And I had someone go, there's undefined behavior in the specification. And I pinged them back and was like, why do you care? And they're like, because my compiler doesn't work. I'm like, what? And they're like, yeah, I've built a Rockstar compiler in Scala, and I don't know whether the empty string is equal to 0 or not. I'm like, I don't know either. This is a joke. You weren't supposed to do it. And it just kind of kept going. It built up this momentum until there were 4 or 5 people all building their own implementations in different languages. And it's like, you know, they wanted me to be the standards committee. I'm like, I'm the project manager of a joke. But it didn't go away. And people sort of kept, you know, referring to me as the creator of the Rockstar programming language. And I thought, I like the way that sounds, but I don't feel like I've earned the right. And the only way to make this right was I spent a couple of weeks over Christmas going way back into my compiler engineering and learned how to build parsers and how to build interpreters. And I built a Rockstar interpreter in JavaScript. The reason I did it in JavaScript is because I wanted to put it on the internet where everyone could just type it in on their phone and write Rockstar, so that everyone could be a certified Rockstar developer. Punch it in, go, there you go, and come and see me afterwards. I'll give you a sticker, and then you're part of the Rockstar developer program. And you can go for all those sweet LinkedIn jobs. The website is here, codewithrockstar.com. Try It is the interactive interpreter. Now, you see that logo up the top there? I wanted something that was pure out, screaming heavy metal. And I looked at all the bands I could find, and none of them were hardcore enough. And then someone said, have you thought about using Microsoft Consumer Products 1980 to 1982 as your inspiration? And I just loved that. I thought it was exactly what I was looking for. So I figured Microsoft aren't using it, so I've recycled their old logo. That's where that came from. Please don't take my MVP away. And yes, there is now the Certified Rockstar Developer Program. Write some code, get a sticker, put it on your laptop. With any luck, in a couple of years, recruiters will stop talking about Rockstar developers because it's a bloody stupid way to hire people. Now, the last thing that I want to do for you today is I want to do an experiment with all of you. So we've seen some computer programs that create pictures and art. And we have seen computer programs which are pictures and art. And we've seen computer programs that create music and songs. And I wanted to be able to write a computer program that was actually also a song, and so I did. And I'm going to perform that for you now. For the first time, the world debut of FizzBuzz in Rockstar. And I want all of you to tell me whether you think it succeeded. You ready?
suppose.
And if anybody ever ships any of that code to production, you're all fired. Understood? See you at the party.